You might not think much of the crisp mouthful of water that refreshes you when you awake from your slumber at 3 a.m. In fact, this abundant and ordinary glass of H2O does a great deal to support life as it is. To understand water's unique properties, we must first take a look at its structure. The molecule H2O is shaped like a V, with two hydrogen atoms on one side and an oxygen atom on the other. This configuration makes the molecule polar, with a negative and a positive end. Since opposite charges attract, the positive hydrogen atom of one water molecule attracts the negative oxygen atom of another molecule, forming a hydrogen bond. As you will soon see, this special form of intermolecular force is crucial for all of water's properties. As a child, you might have wondered why some insects can walk on water and hypothesized that you can do so too by wearing socks dipped in oil. Actually, this phenomenon is due to the cohesion of water. Due to hydrogen bonding, many of the water molecules in a sample of liquid water are linked together at any given moment. Thus, the hydrogen bonds hold the water together, making it more structured than most other liquids. The cohesion of water has many implications. For example, it results in a high surface tension. Normally, molecules are surrounded by other molecules on all sides. As a result, the attractive forces between neighboring molecules cancel each other out, leading to no net force within the liquid. However, at the surface, the molecules are only attracted to each other from below and from the sides, leading to an inward pull toward the bulk of the liquid, causing the surface to contract and behave as if it were under tension, known as surface tension. Hydrogen bonds in water are the strongest intermolecular force, leading to a greater tension than other liquids without hydrogen bonds, and allowing light insects to walk on the water surface. Sure, this phenomenon is fun to observe in a slightly overfilled cup. It might prove advantageous to some insect species, but are there any other greater impacts of cohesion on the ecosystem? Let's first talk about adhesion, another property of water. Adhesion is the clinging of one substance to another. Cohesion and adhesion are useful during water and mineral transport in plants, where evaporation in leaves induces tension at the air-water interface. Water from more hydrated parts of the leaf is pulled towards the area to reduce tension. The upward pull is transmitted through water-conducting cells all the way to the roots, because each water molecule is cohesively bound to the next by hydrogen bonds. In addition, the adhesion of water by hydrogen bonds to the relatively positive molecules of cell walls helps counter the downward pull of gravity. This long-term transport of water and minerals allows the leaves of vascular plants to carry out photosynthesis and other life processes. The next time you seek shade under a tree, remember that its survival and your coolness from the leaves depend on the cohesive and adhesive properties of water.
If you ever watch a rocky launching, you might notice a massive water spray is jetting water below the rocky flames to cool the launching pad down. But why water but not other liquids? The answer also hides inside the hydrogen bonds. When heat exerts power on water to turn it into gas, hydrogen bonds hold the molecules before they can scatter around freely. As we talked about before, hydrogen bonds in the water are the strongest intermolecular force. Since ripping off large amount of hydrogen bonds is energy consuming, this process makes water molecules exceptional in absorbing heat before turning into vapor. As shown from the macro perspective, water has a high specific heat capacity, around 4,200 joules kilograms per degree Celsius, meaning you need to input around 4,200 joules of energy to let 1 kilogram of water rise 1 degree Celsius, or 1.8 degrees Fahrenheit. If you boil 1 liter of water at room temperatures until it completely evaporates, you need around 2.6 million joules of energy. That's about the same energy you need to keep a normal-sized fridge running for 1 month. In short, water's outstanding properties of absorbing heat make it a universal coolant. You can see water's cooling usage not only in the launching pad, but also in air conditioning and the sweating sensor in your skin. People sometimes call water in the universal solvent. This name doesn't come out of nowhere. You could see water dissolving table salt, sugar, juice you split on your shirt, effervescence tables, etc. When a liquid is dissolving something, what it does is pulling molecules from the substance apart. Unlike other liquids, water's property make it exceptionally effective at this task. If you remember, water molecules have a partial positive charge at the hydrogen atoms and a partial negative charge at the oxygen atom. Therefore, they could get between charged molecules and pull them apart using the attractive force created by different charges. I know your smart brain might have some questions about the name universal solvent now, since some counterexamples may have already flown in your mind. Oil, yes. Oil is a great example of something that doesn't dissolve in water. But how? Let's go back to the water molecules. As we mentioned before, water molecules can utilize the attractive force of charges to pull things apart. When molecules you are trying to dissolve are neutral, meaning there are no charged parts, water molecules have nothing for it. That's why waters cannot dissolve all things like oil, your table, the residence building, etc. They all have the neutral molecules on the surface to prevent unwished dissolution by water. For us, the protection layer is our neutral membrane. Next time you are drinking water, appreciate our cells' membrane. Without them, you could be dissolved easily by this mighty solvent like a bottle of salt. Plastic can flow in the water because its density is lower than water. While a piece of pottery could easily sink in the water due to its high density, your middle school science teacher may teach you this common knowledge before. As you may notice, ice could stay at the top of the water, so we could easily derive that ice must have a lower density than water. But why? Here's a zoom-in picture of the water. In its liquid form, water molecules will constantly break and form bonds with each other. Their positions are irregular, are changing constantly. Now that we are done with the water, let's look at the zoom-in picture of ice. When the temperature reaches the freezing point of water, the hydrogen bonds between water molecules become strong and lasting, unlike the faint bonds in the liquid form. It's not hard to spot the inner hexagonal hollow of the structure. This structure is formally called as crystal lattice. This sturdy structure reduces the density of water as water molecules can no longer scatter around. In the natural environment, the density anomaly of water allows those underwater creatures to survive. The floating ice creates a living space underwater. If the ice is heavier than water, fishes will be crushed by the ice once the temperature reaches the freezing point. It's amazing how the small phenomenon like ice cubes floating is a key to survival for the underwater creatures.
You might be a critical thinker, and note that since all the properties mentioned above are due to the hydrogen bond of water, another molecule capable of forming hydrogen bonds can also serve the purpose of water. Let's look at ammonia. Looks kind of similar to water, huh? It is also an abundant small polar molecule capable of forming hydrogen bonds. However, its high reactivity, pH, and toxicity compared to water threaten to harm organisms more than it helps them. Still not convinced? Let's consider hydrogen sulfide. It has an identical structure to water and can act as a solvent. Still, it fails to serve as the foundation of life because it cannot form hydrogen bonds, is very toxic, and has a low pH. To have so many properties essential to supporting life without harming them compacted in a single molecule, water, is no less than a miracle. Looking back, we have covered water's distinctive properties, including cohesion, adhesion, high specific heat, its role as a universal solvent, and its unusual trait of low density as a solid due to hydrogen bonding. Water's unique properties, combined with its benign qualities of being non-toxic and pH neutral, make it the cornerstone of life. I won't delve into the cliche call to action of urging you to conserve water in your daily life. Instead, I simply wanted to express how fortunate we are to have it on our planet, as it gives rise to all the life forms we will ever know. If you watched this far, consider subscribing to Biomedia Club, and we hope to see you next time.